Hey everyone, my name's Arnav, and I'm here to give an outline for ranked choice spoiling from the 2022 NAC. In ranked choice spoiling, you're given N ballots for an election with K candidates. Your task is to insert candidate Z into every ballot such that candidate A is declared the winner of the election. There's two subcases to this problem. Either there are two candidates, K equals 2, or there's three candidates. And we'll consider each case separately. So when k equals 2, there's only two types of ballots, AB or BA. Now the AB ballots you don't really want to change. Candidate A is already winning, we should leave them as is. So let's just throw Z onto the end of those. For the BA ballots, for some of them you want to put Z at the beginning because that'll depress B's votes in the first round. Or you want to put Z at the end because after candidate B is eliminated, you want all of those votes to go to candidate A. So there's actually only three types of ballots to consider once you introduce candidate Z. Every ballot is either ABZ, BAZ, or ZBA. Now, since there's only three types of ballots to consider, you can actually just iterate over every possible way of splitting the ballots and run a simulation in constant time, and that admits a linear time solution to the k equals 2 problem. However, because there's only one kind of decision you need to make, how many BA ballots are moved to candidate Z, you can actually just do some algebra and figure out that candidate A wins if and only if they start with at least a quarter of the first place votes. So that's k equals 2. I went through all of those observations because they'll be helpful for k equals 3. Like I said, simulating can be done in, well, I guess it's k factorial time, but not very much time relative to the number of ballots. We can say constant because k is bounded by 3. However, the number of ways to introduce Z into each ballot has now grown a lot. There's 6 types of ballots instead of just 2. 3 factorial is 6. And there's 4 positions where we can insert Z onto each ballot for 3 degrees of freedom. So if we just naively inserted Z everywhere we could, that's n to the 18 possible elections we need to simulate, which, while polynomial, is going to be too slow for the time limits we have at NAC. However, we can apply some of the same observations we used in the k equals 2 case for the k equals 3 case and bring down this runtime considerably. So the first observation to make is that for every ballot, either Z is at the beginning, it spoils that ballot, or it's at the end. We never actually want to insert Z in the middle. Another observation to make is if A is already winning the ballot, we don't want to spoil the ballot in favor of candidate C. That only hurts us. And so these two observations already take us down from n to the 18 to n to the 4, which is a huge time savings, but it's still too slow when we have 1,000 ballots. The final observation to make, and this one's kind of new for the k equals 3 case, is that if you have a ballot that's BAC and a ballot that's BCA, you want to spoil the BCA ballot before you spoil the BAC ballot. And this is somewhat intuitive when you phrase it in these terms. The BAC ballot is easier in some sense to move to candidate A's pile. So we want to ruin the BCA ballot first. Similarly, you can say the exact same thing by symmetry for CAB ballots versus CBA ballots. And once you make this observation, there's only n squared cases to consider. How many ballots is B winning that need to be spoiled for candidate Z? Now, if you're watching this video, you may ask, how on earth are you supposed to come up with these observations? Well, one method, which is pretty hard in ICPC, is to write a slower brute force and try and look for patterns. So find cases where, find ways of dividing the ballots where candidate A wins. Another is to work out some cases on paper, specifically using the method of exchange arguments, where you can say, okay, if I spoil a BAC ballot, can I switch this spoiled ballot to a BCA ballot and still have the same result? The algebra isn't that interesting, so I've left it off the slides. Also, you should, as an exercise, you should see if you can prove any of these observations for k is greater than 3. They may or may not be true. Hope you had fun with this problem.